Hello, welcome to lesson number 4. My name is Thomas Enuru. In today's lesson, we shall be learning Introduction to Earth Observation Data and Products and Services. So, we shall look at the course outline. In this lesson, we are going to cover definitions, what Earth observation data capture process look like. We're also going to learn something about advantages of Earth observation data, study characteristics of Earth observation data, look at the major Earth observation data sources, and then finally understand or learn the application of Earth observation data and services. We'll start by looking at the definition of Earth science. This is any science which could be geology, meteorology, oceanography, etc., that deal with the Earth and with one or more of its parts. So under Earth science, we have Earth observation science, which is a science of gathering information about the planet's physical, chemical, and biological systems via remote sensing technologies, which usually deal with satellites carrying image devices or sensors. So within the Earth science and under remote sensing, there originates the Earth observation science. So Earth observation science under remote sensing technologies is a small component within that. In summary, we want to see how is Earth observation data, basically EO, captured. In the process, A represents the energy source. So in this case, our energy source is the sun. The sun releases or gives out radiation in part B, which radiation interacts with the objects in part C on the surface of the planet or the Earth. And some of the energy or the radiation that is from the sun is absorbed while others is reflected. The other energy source is also from the satellites themselves. So these are active satellites that send energy or generate energy and then propels or sends it to the Earth. And this energy interacts with the object, which either is absorbed or reflected. When this energy is reflected both from the sun and from the satellite themselves, this information in terms of electromagnetic spectrum is captured or detected by the sensors within the satellites. And the satellite relays in one part this information to another satellite, and or it relays this information back to the receiving station. Within the receiving station, the information that has been sent by the satellite is interpreted and analyzed. The interpreted and analyzed information is generated in terms of images, for example, or it could be in terms of maps, are later used in application of, for example, managing natural resources. They could be used in agriculture. They could be used in emergencies, responses, activities, as well as um, in disaster management. So this process of capturing data and then converting it into a product, and our product in this case is Earth observation data, happens daily with the sensors or the satellites uh, products that we'll see in subsequent slides. So as far as vulnerability of wetlands is concerned, why are we interested in Earth observation? It's because this is a space-based technology that delivers reliable and repeated coverage datasets. So giving an example of Landsat, for example, um, program. This has been in operation from as early as 1972, 71, 72. And up to now, we have this information repeatedly being supplied or distributed to us after every 16 days. So the reason why we are interested in Earth observation is because it has the capability or the technology of delivering reliable and temporal data sets for different applications that has been mentioned earlier. Also, the Earth observation technologies have ability to collect information of a large spatial area. So, for example, if you are to use a drone, let's say, to capture an image that covers, let's say, a district as your spatial area, you'll have to spend, depending on the capability of that drone, or if you're using a camera, it will depend, might take you about a week or so to capture an image of that covers a district spatial area, for example. And now if you look at the covering a country, a national spatial area, you might have to spend a few months to do this. But with Earth observation technologies that utilize the satellites, in this case, you will be able to obtain information that covers a large area in a very short period of time. The other reason for us being interested in Earth observation is because surface areas and objects are monitored over time. So the aspect of monitoring is very key in the science of Earth observation, because we can be able to see changes that has occurred on the surface or Earth objects, and in this case, let's say wetlands, for example, over time. And then we can also be able to see what are these factors and how have they been changing over time? Have they been increasing, or are others decreasing? So in relation to wetland vulnerability analysis, Earth observation provides affordable data sets that are suitable for assessment of a widely differing spatial scales from individual wetlands through national to regional coverage as well as the global level. These Earth observation technologies have also abilities for processing large quantity of data covering a wetland. And through that, we can be able to perform vulnerability assessment or analysis in a poised and advanced processes. It's becoming very popular and attractive, especially in wetlands, especially in remote areas as well, that Earth observation provides a low-cost method of assessing wetlands in the fields, which would be prohibited in terms of cost as well as logistics. It's noted that while Earth observation is an important input to wetland inventory, assessment, and monitoring, knowledge of the local context and the collection of in-situ data remains critical for ensuring locally relevant outputs. So in the previous slide, we spoke and explained a lot about the advantages of utilizing the Earth observation data. But having these products alone does not give you the best credibility in analysis, but rather the knowledge of the local communities, stakeholders, experts in national wetlands is very key for one to generate the best outputs during the analysis. We want to look at a few things about this Earth observation data. One, the sensors that are on Earth observation systems, the EO systems, which, for example, are the satellites, they usually record what we call electromagnetic radiation. So in the first slides, we mentioned that the sun gives out electromagnetic radiation, which interacts with the objects on the surface of the Earth. And this information or the radiation is collected by or recorded by the EO systems. So in other words, these EO systems are made up of detectors that record specific wavelengths of electromagnetic radiation. Now, in this lesson, we are not going to dive so much deep into understanding the concept of the wavelength of the electromagnetic spectrum. But we know we should quickly understand that every object has a capability of giving out energy or absorbing energy within a varying wavelength of electromagnetic spectrum. So the ability of these sensors to record the different sections of electromagnetic spectrum in terms of their wavelength and frequencies is what gives a thumb up for the Earth observation sensors. And through this, we can be able to measure and monitor the different components of the wetlands to guide on the vulnerability analysis. The other aspect is that when radiation interacts with the matter, some wavelengths are absorbed and others are reflected. This is just the same thing that we mentioned earlier about how and through what process this radiation that is released from the object or from the sun interacts with the object on the surface of the earth. Therefore, for one to utilize the earth observation data to measure the different and monitor different objects on the surface of the earth, they need to understand which wavelength the different objects and features of the earth lies the particular electromagnetic strength. In this case, if you look at the vegetation, you could view it much more within the infrared region of electromagnetic radiation or spectrum, and this has a particular wavelength within the spectrum, and then also for the other features. So for this lesson, what we need to summarize to understand is that the radiation that is given out by the sun has a wide range of wavelengths, and within a certain specific part of the wavelength of the spectrum, along the wavelength, other features absorbs and reflect the different parts of the electromagnetic spectrum, which is recorded using the Earth observation sensors. And for one to perform analysis with the Earth observation data, they need to understand which area of electromagnetic spectrum and what wavelength they are dealing with, so that they can understand the particular feature of the Earth that they are dealing with. The other key characteristics or the parameters of Earth observation data is the resolution. Now, resolution is a number of pixels that can be displayed on a device, or the area on the ground that a pixel represents in an image. Think of it this way. If you look at a house, the house with a large number of pixels, you can be able to tell the corners within that house. So in other words, the number of pixels it will have will give you ability, or will give the device that you're looking at the house, which is an image in this case now, to clearly distinguish between which object you're looking at and the corners it has. This aspect is so much generated in the newly developed mobile devices or the smartphones that we have, in that when you buying a phone or a camera with a large, what is called the value for the megapixels of the camera, you will find that the cost of that camera or the smartphone will be higher than the one with the lower megapixels. So this is basically telling you that your phone has ability to store many pixels for the image that, or the data that you're capturing, so that you can quickly distinguish between the objects you will have captured using that device. However, within the Earth observation data, there is more to this aspect of resolution. The first is the spectral aspect which looks at the specific wavelength intervals that a sensor can record. What does this mean? That within the wavelength or within the electromagnetic spectrum or radiation, there are different specific wavelengths. Talk about the infrared, the microwave, the visible range, and so forth within the electromagnetic spectrum. If a sensor, if the Earth observation system has ability to record and understand the specific wavelengths intervals of the objects that are releasing the energy, then in that case we are looking at the spectral resolution of that sensor. There is also the second part of the spatial resolution. The spatial resolution looks at the area on the ground represented by each pixel. So basically it is telling us that when you look at the area, when you look at the object on the ground, the size of the pixels that is being covered within your device of that object is the spatial resolution of that image or sensor. So in other words, an image which has a higher number of pixels to represent an object, let's say a house, the higher will the spatial resolution of that object and vice versa. The third aspect of the resolution, particularly for Earth observation systems, is radiometric resolution. This looks at the number of possible data file values in each band. Now, the band is indicated by the number of bits into which the recorded energy is divided. This is a very lengthy part to understand, which we will not talk much about. But all you need to understand is that if the number of possible data file values an object has, the more one can be able to distinguish between this object with the other. The temporal resolution aspect of the Earth observation data system looks at how often a sensor obtains imagery for a particular area. So here we are talking about if wherever you are right now, the Earth observation system images that part of where you are. The temporal resolution looks at how long it will take the sensor to image that particular place another time. So if it takes 2 days, then the temporal resolution is in 2 daily intervals. If it is 1 day, then it is daily. So in other words, the lower the number of days, the higher the temporal resolution, and the higher the number of days, the lower is the temporal resolution of that sensor. Now, for the sake of Earth observation data application, we need to look at over the decades which Earth observation systems or satellites are commonly used. So in this chart or figure, we'll see that we have on your lower left corner, you'll see Landsat's sensors or satellite systems represented, Sentinel represented. On the middle part, you'll see Rapid Eye and Flock 1. Flock 1 is towards your right, mid-right. And then on the top, mid, you'll see Worldview Earth Observation Satellite Systems, SuperView 1, Sport, Eros B, SkySight, and so forth. Now, if you look at the image, the picture again, you'll see that it has a scale. So the scale on the vertical scale is the resolution. The horizontal scale is the revisit time. Also on your lower right corner, you will see the spacecraft mass. In other words, the mass of the spacecraft. The spacecraft is an object that carries the satellite sensor, or it's the satellite system itself. So we have a range from 3,000 to 3 kilograms. 3,000 kilograms to 3 kilograms. At the lowermost right-hand corner, you'll see the average data prices in kilometers squared, in dollar per kilometer squared or square kilometer. So understanding that legend, let's go back and understand the different commonly used Earth observation satellite systems. So we see that Landsat 8 has a lower revisit time and also has a resolution which is a little bit high. So when you see on the vertical scale, you'll see that 10-meter resolution is high compared to a 1 resolution, which is on the top part of the scale. So Landsat 8 has a low revisit time, but which is between a week or is weekly, but has a poor spatial resolution of about 10 meters. Sentinel, on the other side, is having close to between weekly and daily revisit time, but the resolution is more improved compared to Landsat 8. Flock 1 on the mid-right is rather having a less revisit time, which is more like hourly, if I could say, hourly, and with a moderately high resolution, spatial resolution. Then when we look at, pick an example of GeoEye, GeoEye has between a week and daily revisit time and a very high spatial resolution of 1 meter. And that is the same for Worldview, which is daily and a high resolution of 1 meter. So we can see that the different satellites have the ability of having both a high spatial resolution and a high revisit time, in other words, the temporal resolution. But for others, you will have a high um, a high revisit time, but a low resolution. For example, the Flock 1. For Sentinel-8, no, Landsat 8, sorry, rather, you'll find that it has both poor spatial resolution and a high temporal resolution, because weekly is higher compared to hourly or daily in terms of temporal resolution or revisit time. We dive more onto application of these satellites and also look at more on the characteristics of of different satellites. Now, on the scale, you'll see that we have the temporal resolution, which is more like a swap of the earlier slide in terms of the scale. And on the lower scale, you have the spatial resolution. Now, the spatial resolution is increasing from right to left, and then the temporal resolution is increasing from bottom to top. Now, let's pick an example of the different application of these satellites. We'll see that climate application is okay with a low spatial resolution of about 10 kilometers, but a high spatial resolution in terms of uh, rather it takes in it's applicable in for satellites that have a low spatial resolution and spatial and temporal resolution. On the other hand, with emergency response application, need a satellite with a high spatial resolution, a higher temporal resolution, but a low spectral resolution and a high radiometric resolution. In agriculture application, you'll need an image which has moderate spatial resolution, moderate temporal resolution of between 4 days to let's say maybe a 20-day temporal resolution, and then you'll need a moderate spectral resolution and radiometric resolution. So it's a balance of the four. Urban infrastructure requires data with a slightly more spatial resolution so that you can be able to distinguish different objects, the houses, the roads, and so forth. And a slightly low temporal resolution, but with a high spectral resolution and a high radiometric resolution. For weather you will need a satellite with a satellite product with a low spatial resolution, but the one with a high revisit time, in other words, the temporal resolution of between 1 hour to 4 days, so that you will see the patterns of the change in the weather condition. The spectral resolution also has to be high, but radiometric resolution can be lower because it will require data sets that is having the radiometric resolution of between 16 to 34 bits of data. So if we look at in terms of the different Earth observation satellites, we see that for weather, AVHRR and CYFI waves are actually used a lot in the weather data, and because they have low resolution but with high temporal resolution and spectral resolution in them. Geology and topography, the satellites that are mostly used in there are the QuickBirds satellite products, airborne cameras, and the reason is because they have a very high spatial resolution, temporal resolution, high spatial resolution but low temporal resolution, and low spectral resolution. But on the other hand, they have a very high radiometric resolution in terms of the data bits. In this lesson, we are not going to learn so much about this, but you're free to look up for details and also digest more on this image. Now, we will look at the different sources of Earth observation data. Here we can check out a few. The ESA, the European Space Agency, providing the Sentinel data, is one of the freely accessible sources of public Earth observation data. The Joint Research Center, also in Europe, is providing a lot of Earth observation data under the E-Station program, or the G Global Monitoring for Environmental Science and Security, is also providing data through the E-Station products or program. Copernicus is also a program of EU, which is also providing a lot of Earth observation data. EUMETSAT, working together with the E-Station program, or the GRC E-Station program, is also one of the public domains providing free access to Earth observation data. The Landsat program, which is the longest freely distributed Earth observation data or satellite images, is also one of the free sources we have. The NOAA source and NASA. We have the Japan sources, China and India. They also provide this Earth observation data. So feel free to click to copy or to be able to access this slide within the document area of the e-learning platform, to access all this, or type in your browser and try and access these platforms. remember that before you can be able to be given rights to download the data, you have to register with the different the data providers so that your credentials are approved and you can be able to download the data sets from the sites. The other commercial sources that are publicly available include the Digital Globe resellers, the Airbus, Planet Labs, the EGOS, Satellite Imaging Corporation, European Space Imaging, the Land Information, Terra Server, and Apollo Mapping. So if you're working for an institution, of course, most of these commercial sources, the products are well improved. Some have a very, very high spatial resolution. So depending on your application or what you're trying to do, you're free to check out the sites. And also in terms of affordability, if your institution can be able to afford this data, then you can be able to access them. But nonetheless, you should know that if you're performing, you're going to conduct wetland vulnerability analysis, going with the public freely accessed sources is good enough, as we shall see in the later lessons under data processing for wetland vulnerability analysis. You will see that most of the data sets that are being provided or that are being used in that lesson are all freely available in the different public domains that you can access after doing a registration with the platform or the providers. In here, feel free within the e-learning platform to give us your questions, and then also go to the discussion section of the lesson or the course, and then put down your discussion needs, the questions that you need answers to be responded on, as well as your opinion about the course, whether most of the things that you expected to see, you saw, or we didn't provide much. Please note that this lesson or the session was not to study all aspects of remote sensing, but just to give a recap of how important Earth observation is as far as wetland vulnerability analysis is concerned. So thank you very much again for your audience and for your time. Thank you.